Hi, folks. Welcome to the 158th episode of the Qiskit Quantum Seminar. As is tradition, why don't you let us know where you're tuning in from in the chat? I highly recommend playing with the chat now because it is where I will read out any questions you may have during the talk. And I'll kick us off. I am Ed Chen, a research scientist at IBM Quantum, and I'm hosting this seminar from Research Triangle Park, North Carolina. While people familiarize themselves with the chat to share where they're from, I have a reminder that this seminar takes place every Friday at noon Eastern and will be hosted on this Qiskit YouTube channel. We have a great lineup of invited speakers every week for the next few months, actually. And of course, I do want to acknowledge all the care and effort that goes into these seminars, thanking our producers, Lako Minev, video producer Paul Searle, and managing producer Olivia Lanes. Let me just take a look at the chat and see where everyone's dialing in from. I see Vipul from, Paul's obviously from Oregon. He's our solid. Jorge from Madrid, Elite from Chicago, Mikhail from Poland, Mitch Agua from Argentina, Mitch from Georgia. Nice. A good range of places. Anyways, today we'll be hearing a talk by Philipp Schleich, who will be speaking to us about bypassing the hardness of ground state preparation and simulating chemical dynamics. Philipp is a PhD student in computer science at the University of Toronto, supervised by Alon Esbru-Guzik. His main research interest is the complexity of simulating physical problems on quantum computers. He mostly focuses on simulation problems from chemistry and quantum algorithms for differential equations, and has also undertaken work together with Dominic Berry and Nathan Wiebe. And Philipp asked that folks interrupt with questions in the chat to follow along, and if I'll read your questions out loud as they come in. And so please, Philipp, take it away.
Thanks for the introduction, and hi everybody. Thanks for tuning in. Let me know if you have any trouble seeing my screen. Okay, so I'm gonna talk to you about some exciting recent work of us trying to bypass the hardness of ground state preparation and simulating chemistry and quantum computers. I'll start off with a short introduction what I mean with like quantum computational chemistry in the context of the talk and like setting up the problem, what our idea was, what can we do with dynamics, and then sum up in the end. Okay, quantum computational chemistry for like the rest of this talk, at least today, will be anything that treats a molecular Hamiltonian on a quantum computer. And a molecular Hamiltonian could look like this, which is composed of a kinetic energy of a set of particles like electrons, then the kinetic energy of nuclei, if we were talking about non-Born Oppenheimer dynamics, and then interactions between the electron and nuclei, interactions within the electrons, Toulouse Coulomb interaction, and then also interactions within the nuclei. And treating computationally means thinking about the spectral properties. In particular, this would be the minimum eigenvalue, so this ground state that everybody talks about, and then time evolution, as in like going from some initial state to a state after some time t. And there have been three, among many others, but like three essential developments that make quantum chemistry possible on quantum computers. One ingredient is that Seth Lloyd has proven, like in 1996, that the simulation of k-local Hamiltonians is efficient. That means we have a Hamiltonian that is a linear combination of operators, which are Hermitian, and each of these operators only act non-trivially on at most k qubits, or like k individual subsystems. And then we also have an algorithm from 1995 by Kitaev that allows us to extract the eigenphases of a unitary from a state. That means we can like extract these phi j's. And then we also know that if we take Hamiltonian simulation, which looks like this, then we have eigenvalues associated to this Hamiltonian. Then we can use this algorithm to extract spectral properties. So for instance, the ground state, if we also use the fact that the simulation is something efficient. But there's a problem to this, and that is that this together to work requires sufficient overlap with the eigenstates of interest. And in our case, that would be the ground state. So we need sufficient overlap in the initial of like this phase estimation algorithm. Like in this initial state psi, we need sufficient overlap for this to have a success probability that we can work with. One of the problems here is that the k-local Hamiltonian problem, as opposed to the simulation of k-local Hamiltonians, is QMA hard. That means finding this ground state, or like deciding whether the ground state is like below a certain threshold, is not efficient. So we cannot make any predictions about efficiency, and in the worst case, that would be exponentially hard. And the other thing is that there was a recent work trying to find, or like trying to investigate heuristics to find such initial states, either quantumly or like classically, and they haven't. So in their study, they basically conjectured that most systems would run into the problem of having an exponentially vanishing overlap with the system size. There might be a few individual systems that don't have this issue, but generally, if we try to do chemistry this way, it is suspected that we will run into this overlap problem, and that would make any efficiency claims pretty much useless. So what do we want to do instead? Okay. We can also look at like other ways how quantum chemistry is done, and most of these ways will be reliant on good input heuristics. So like a few of the main algorithms are imaginary time evolution type, VQE type, and like phase estimation type. And we already talked about phase estimation. So if you don't have a good overlap, the success probability will be too low, like the success probability to find such a ground state. So we cannot really use this if you don't have a good overlap. For variational quantum eigensolvers, and I think people watching the Qiskit seminar probably have seen VQE quite a few times, but just to quickly reiterate, in VQE, you would start with a parametrized quantum circuit that serves as a trial wave function, and then you try to optimize the expectation value of this trial wave function with respect to the Hamiltonian. And then the minimum of that would serve as an approximation to the ground state of this Hamiltonian. And this is limited by the hardness of the optimization, and this would run into these barren plateau problems of vanishing gradients. And this again, if we have a good initial state that has a good overlap, this would be easier. And then the other thing I wanted to mention was imaginary time evolution type algorithms, which are similar to power iterations. And again, for this to be possible to converge, we need a good input state. One way out of this, I've got this dissipative-ish methods, where quite a few of them have popped up within the last year, which was not really like basically parallel to like our thoughts to do like chemistry-inspired input state preparation. So all of these somehow use a heuristics to not as like what these methods kind of have in common is we start with something which has a good overlap, and then we kind of try to restrict into this good overlap space. Whereas these methods, instead of taking something bigger and going to the small overlap space, they try to move towards the small overlap space without like losing probability amplitudes in a wider sense. So like one of them would be, for example, inspired by a Lindblad open system simulation using jump operators to move towards the ground state, or like a dynamical cooling algorithm. And so for the Lindblad type ground state preparation, the input heuristic is like the choice of these jump operators. For the dynamical cooling, there's a heuristic in terms of what perturbation method that is used. So our idea is similar to this, trying not to stay within the like overlap of the exact ground state, but try to do something with heuristics. And then let me maybe take a step back with like what we can do. Like, let's suppose we have a ground state, and then one thing one could do with that for a wide range of applications, such as reaction rates, photochemistry, and spectroscopy of free energies. You can do something useful if you have the time evolution of that. Or if you take this as an input state to a subsequent time evolution. And then we can take as an example, trying to find the reaction rates of, let's say we have a system A, we have a system B, and then go through some open system time evolution that is supposed to couple system A and B, and that represents a chemical reaction. And we get a state as an output, which is like a product that combined A, B, and something that is not a product. So if we had an oracle that marks which is a product and which is not a product, we can use that to extract how much of the system, like let's say that, so this amplitude A has reacted, and we can use this as a surrogate to measure the reaction rate. And this is how we can use such a time evolution, and based on like some sort of meaningful input states. And ground states here serve as meaningful input states because it's like one of the things people like to prepare. So our goal is to give input states that we can construct efficiently, but they don't necessarily need to be ground states, and they don't necessarily need to inherit the hardness of these ground states. But we still want to give input states which are reasonable, so that if you look at this reaction rate simulation, A and B still mean something chemically sensible. Right. And then just to sum this up briefly, we've seen that eigenvalue estimation for local Hamiltonian is hard. And in fact, in reality, chemical systems rarely would ever cool down by themselves to the ground state unless someone tries to build a quantum computer. But we know that k-local Hamiltonians are efficiently simulatable. And then there's even evidence that for mean field dynamics, there's a quantum speedup for simulation. So this is very encouraging to use simulation. And our idea is to use simulation as close as possible to something that would happen in a chemistry lab. Right. So what we propose to do is an input heuristics based on a scattering scheme. We want something that in the end is efficient. Something we require is access to a set of ground states, but so that might seem a bit counterintuitive. We say we don't want ground states, but then we require like access to a few ground states. But what we require is access to a set of ground states that is of a fixed system size. So any argument that the overlap would exponentially vanish with like increased system size doesn't really hold for atoms, because if you look at the periodic table, there is a set number, and that is likely not to increase very much. And if you think of like what, let's say, organic chemists care about, that is again like only a small subset of the periodic table, and then it's not that unreasonable to assume we can prepare the ground states of like a set of chemically interesting atoms rather than molecules. And then Alan had the idea to take inspiration from the ab initio nanoreactor, which is a computational tool that tries to prepare rather unphysical situations to synthesize, but not physically, but like computationally synthesize like things you want to display on a computer and like kind of study, but you cannot really do that in a lab. And then we thought like maybe we can do this on a quantum computer too. And another work that inspired us for that was an experimental work from 2018 that took two hydrogen atoms and like two physical hydrogen atoms and then scattered them together. And if you do that, there's a bounded probability of like roughly 30% that this succeeds and actually forms a hydrogen molecule. So our idea was to like, why not think about doing this on a quantum computer? And then use the result of this as like an input to the to like a larger computation. So let's say we have access to these like small input states, and then we want to build like a larger molecule. Then we need to implement the scatterings, and then we can like think about this in terms of a tree structure here. So every node in this tree would correspond to some simulation that takes, let's say, A and B, and gives us the next node with a specific success probability. And one of them forms something that we want, one of them doesn't. And again, this also implies that we have some kind of oracle that like marks the success here. The problem here is that if we have like a probability p at every one of them, this still leads to an exponentially vanishing success probability in the tree depth. So if we want to construct complex molecules from that, this is not really a good way to go. So we thought about how to approach this, and the naive, obvious way to do this on a quantum computer is like we can do amplitude amplification, and that might do it. However, standard amplitude amplification is not good enough because we don't want to do these reflections always around the start, but we want to do like local reflections so that we don't have to basically for every amplification rerun the entire simulation, which kind of corresponds to this case. So then what has been developed in particular for block encodings was this oblivious amplitude amplification. And what this can do is do amplitude amplification, but for any input state. So in this depiction here, if we look at amplitude amplification by itself, we start with this 0 input state. And then there's an algorithm that gives a result that has overlap in the good and in the bad subspace. And then these reflections increase the overlap with the good subspace. For oblivious amplitude amplification, we can do any input state phi, and then we can still construct such reflections. The issue here is, though, that in our case, this doesn't work because the probability for our simulations is state dependent. But this theta 0 here in the assumptions for like oblivious amplitude amplification to work must not be state dependent. So we cannot really use amplitude amplification schemes. And so what we came up with instead was a repeat until success scheme, which I'm showing down here. Right, just to repeat, so we cannot do amplitude amplification because we don't want to reflect around the initial state all the time. And we cannot do oblivious because we have a state-dependent overlap or a state-dependent probability. So what our idea is, and I am explaining this more here, is we have any node in the scattering tree that I was showing before, and then running the simulation that is supposed to combine, let's say, two nodes into the next one in the tree. We get some overlap in a good space, some overlap in a bad space, and maybe some coherence, which, however, is not relevant for measurement. And then if we think about like using first quantization and a position basis to encode our state, then something we could do is we could construct an oracle that determines the success by storing into an ancilla whether a bond has been formed or not. And one way to do this would be by constructing this oracle so that it looks at like how spatially close they are. So like if hydrogen A and hydrogen B are close enough after the reaction, then we can say a reaction has like this scattering was successful. So if we, so what we do then is constructing a weak measurement that projects into the good and the bad subspace, but still doesn't disturb the state enough so that we cannot keep the computation. So if scattering was successful, we're in the good subspace, everything's fine, we can continue. If it wasn't successful, what we can do then, or like what our idea is then is repeat the simulation in the sense that we want to make another scattering happen, like another attempt for scattering. And then if we, so the idea is in some sense, trying to take the hydrogens and just throwing them onto each other often enough until it happens. And then if we have a bounded success probability on this forming a bond, we only need like 1 over this lower bound on the success probability repetitions, and this is successful. How do we ensure that there's such a minimum success probability? And like the rough idea here is that, let's say we have 2 hydrogens and we add like an artificial potential. And the idea for that is also coming from like something that is very popular these days are neutral atoms, as probably many people have heard. And then neutral atoms are like moved around in like a neutral atom quantum computer by optical tweezers. So you take like lasers and like move them around. So we can also construct such a potential with like something that is coming from a modeled photonic field, so that like we can move them together and also like keep them together in a sense. And one thing to also note here is that this is not meant to be like a very strong infinite potential wall, so that they would bump off the wall and then go together. It should be something more mellow. And the reason for that is that this needs to be constructed in a way that it doesn't increase the computational cost significantly. So if we add this purple potential to the simulation, that means the normalization factor of block encoding of these Hamiltonians, which dictates the cost of the simulation in the end, will increase as well. So the interaction that usually is the biggest contribution to this normalization factor is coming from the maximum Coulomb forces that need to be represented, which are basically like these electron-electron interactions on like the smallest grid spacing. It's like if you have an interaction that goes as 1 over the distance, and then you move things very close together and they don't want to be together, then that smallest grid spacing would dictate this maximum, this like strongest force that influences this normalization factor. So we don't want to create a situation that like is even stronger than that. And like something that looks like a harmonic oscillator potential, for instance, wouldn't be that bad. So this is why I've been drawing this like roughly that it looks like a harmonic oscillator.
Philip, we have a question in the chat. I think
Okay.
somebody was saying, great talk so far. Are you treating both the nuclei and electrons in the real space basis, since you are throwing atoms together, essentially?
Right, like, yeah, we're thinking of non-Born-Oppenheimer, like everything currently and everything in real space, yeah.
Okay, thank you.
Which, again, like, obviously has, like, consequences on, like, how long the simulation would need to run. And, like, we cannot really simulate that yet. Okay, then maybe let me get to the like overall computational scheme that we suggest. And I do like this figure, but it has led to sometimes confusion. So I'm trying to build it up like slowly. So in the end, what we want is we have a state preparation we call molecular factory, and then this evolution which resembles like the chemical system, like the chemical phenomenon, which might already be like a scattering in here, but okay, and then a measurement that extracts some quantities. So what we want at the end of the molecule factory is a molecular state, and that, as I said, this molecular state does not necessarily need to be a ground state. It just needs to be like a physically sensible molecular state that can then go into a reaction. Right. Then as a part of this, we need these initial ground states. So each of these registers here is actually another subroutine, like another subalgorithm that calls, let's say, a phase estimation subroutine. And then these go into like these small evolutions, which might be open system evolution. So maybe that's not necessarily the best way to write this. And then all of this would be embedded in like a modification of the Hamiltonian through like an external bath, which one could do explicitly in the Hamiltonian, but we would rather use open systems algorithms, which like many of these like have been popping up like last year especially. And then these external potentials that are meant to increase the success probability of these scatterings. And then also like adding photonic fields through modifications in the Hamiltonian that are ultimately probably necessary if you want to represent chemical reactions. So, and in the end, yeah, they would go into this evolution. And then if we think of what kind of chemistry would fall into this scheme, as I already mentioned, like we can think of reaction rates. So that requires an observable across the final state after the dynamics. So we only need to prepare the final state and then construct an observable that has support over more points on like position space. And then situations like photochemistry and spectroscopy rely mostly on time correlation functions. So the issue here then is one would need to create a history state, and that requires like far more qubits. But then ultimately you can also construct observables that go across time steps. And then the last idea would be free energies. I will say more about that on the next slide. So for free energies, what one can do is, or like what, like a computational way to get these would be an ensemble of permuted Hamiltonians. So we have just a set of Hamiltonians, and then we need to encode every Hamiltonian individually, of course. And then for every Hamiltonian, one simulates along a reaction coordinate. And in the end, one can construct an observable representing this ensemble average of energy differences. So we take for every Hamiltonian in this ensemble, we compute the expectation value at like final of the energy at final time minus initial time. Right. And like this would also be able to fall into like all of these applications would be able to fall into like just this overarching scheme here. Okay. And I'm already running towards the end. So just to sum up, we propose to circumvent the ground state or like the overlap problem in chemistry by dynamics, and more specifically by using dynamics to create input states in a way as one could create them also in a lab, with like as much like chemical intuition as possible, as opposed to like trying to like as like many other schemes are doing it like with like, let's call it like mathematical intuition. Sorry. And Outlook, like one thing is of course waiting for a fault-tolerant quantum computer to test this on a larger scale. Until then, one thing I would like to do is finish a numerical implementation of this in a very small scale, which then might only be like this part, but trying to implement this for like the hydrogen example. Another thing that I would say is very important are resource estimates, in order to judge whether like how long specific examples would actually take. So the thing for that is that with the way that with fault tolerant, like the error correction overhead and everything that we're facing at the moment, even if we had a quantum computer, is that I remember at the March meeting, Guang Halo mentioned that any situation where there would be a crossover point of quantum computers being faster is in like a computation in order of days or weeks, with like the estimates for clock speeds and error correction overhead that they used. And if we think about this, then a computation approach that I would take on like classical systems of just like trying around and then running it is probably not good enough, but one needs to be a little more sure that I actually want to run this and this is what I can expect. So like reliable resource estimates for that should be very important. And then also trying to improve the algorithms to lower these times overall. Okay, and that's it. And yeah, thanks to my collaborators.
Awesome. Thank you, Philip.
Okay, should I get back here?
All right. So I think we have another question that came up at the
Okay.
end from Hans Chan. Is there a risk that in this approach, the repeat until success weak measurement can suppress advantages gained from the Hamiltonian simulation?
Can you repeat that?
Yeah. Is there a risk that in your approach, the repeat until success weak measurements can suppress advantages gained from the Hamiltonian simulation?
I think not directly from the Hamiltonian simulation, but I think setting this up generally is a very system dependent. So it's not that one can just generally put parameters, but I think these would be hyperparameters that need to be tuned for every system.
Mm-hmm.
So it's more of a, if you don't choose the right potential, it's not going to succeed situation.
Uh-huh. So actually, that ties in nicely to a question I have about this, which is there's no verifiability or anything in this approach,
No,
right?
no, not that I can see. No. I think that, yeah, it's quite heuristic. Yeah.
Got it.
Um,
Yeah, okay. And very much meant for the fault tolerant era. It
yeah,
seems.
yeah.
Yeah, given how the
I,
depth.
I I don't see how it could be a near-term algorithm.
Yeah, yeah,
Yeah.
yeah.
This is
Great.
also a bit like, so there was a paper like 2 years ago by Simon Benjamin's group that emulated a first quantized grid space algorithm for and they did a scattering of 2 electrons,
Uh-huh.
which took 26 qubits.
Uh-huh.
And then if you already want to scale that up for hydrogen, including the nuclei, it's kind of crossing the boundaries of what you can simulate on like
Hmm. Oh,
easily accessible hardware, classical hardware.
I see. Oh, you'll have to send me that reference. I'll take a look. But all right. I think. Oh, Hans said that was their paper. So thanks for the
Oh,
shout
nice.
out.
Okay.
Good. So Hans can drop it in the chat then. Oh, okay, good.
Yeah.
Ryan. All right. We'll take one last question here. Um, so I have from Ryan. I have an elementary question as someone that's new to quantum computational simulations. What is the reference to the Hamiltonian here? As I understood it, is it perhaps an analog to voltage in a transistor? Um,
I don't think so. Um, mm,
yeah.
no, I don't think I have enough reliable physics background to give a good answer. But the the Hamiltonian is rather something that describes the entire system and all of their interactions, and it's not
Mm-hmm.
like a measure like the voltage.
Mm-hmm. Mm-hmm.
It's more like the electrical circuit for it, I guess.
Mm-hmm. Mm-hmm. That's a good way of saying it. Yep. All right. Thanks. Thank you, Philip, for a wonderful talk. I want to uh, before people tune out, please hit subscribe now to make sure you don't miss next week's talk by Professor Charles Chow from Virginia Tech on building quantum codes from quantum Legos. All right. All right. Thank you, Philip, again from the University of Toronto. All right. Thanks, everyone.